time we will use the 1D advection equation to explain the concept of inflow and outflow boundaries. Okay, so this is the 1D advection equation we have used for a few weeks now, and then we know that there is a general solution for this advection equation. So any function, any shape in terms of x minus ct can fulfill this advection equation. Okay, and then we know that in the model for x within 0 to L, we can determine the values of u. Okay, and how do we do that? We depend on the values of the initial condition, which is the values at t equals to 0, and then we also depend on the boundary conditions, which are the values of x equal to 0 in the following time step, and then also the values at x equal to L, so the boundaries on the sides. Okay, and these are called the boundary conditions, and then we can use the green dots and then the red dots to determine the value of all the dots in between. Okay, so how do we decide, how do we find the expression for the middle values in terms of the initial condition and then the boundary condition? That's what we need to find out in this lecture. Okay, so we know that u is constant along the x minus ct value, x0. So the initial data, the green dots, will uniquely determine the u values in a gray triangle. So why is that? Because the x minus ct is actually this line. And you can see that if you have a shape looking like this, it will shift according to the value of c, which means that the things in this slope will be the same. Okay, this is t dimension and this is x. So you can draw any slope in this gray area, and you can trace it all back to the initial condition, which means that your initial conditions will determine anything within this triangle. Okay, so because we have decided that c is larger than 0, so the inflow is on the left side and then the outflow is on the right side. Okay, and then we immediately know that the thing in the white box will be determined by the boundary condition you applied, because if you draw a line from this red dot, you will see that because it's constant along x minus ct, then you draw a line here, you know that all the values on this line will be determined by this dot. Okay, so we know that the values here will determine the rest of the region, which is the white region here, and the boundary condition must be determined as x equal to 0. So here, the dots here. And in here, which is the outflow boundary, we have a few options here. It can be determined by the advection equation. You can always do the space differencing and time differencing, because it can depend on the values in the initial condition. Okay, so it depends on the values of the initial condition and also the boundary condition at x equal to 0 and t equal to 0, which is also the initial condition and boundary condition at the same time. Okay, so in summary, the data at x equal to 0 and at different times, so the values in this column, the boundary conditions on the left side will affect the white area, and then the initial data, which are the green dots here, will affect the gray area. Okay, so we have to talk about some concepts for the inflow boundaries. So in here, we need to prescribe the data where x equal to 0 and for all the time steps, because they will affect all the values in the white triangle here for all time, okay? And I have to do some calculation now, okay? So if we separate the x dependent part from the waveform or the wave solution, x, so the values of u depend on x and t. If we separate the x dependent part, iota k x minus omega t, and we only consider the real part, and then we can rewrite the equation. Minus iota omega t. Okay, so RE here means taking out the real part. Oh, sorry. So this part is x depending component. Okay. And then why do we write that? Because for the if this is x and this is t, and then if this is 0, and if we want to apply a boundary condition in here where x equal to 0, and then for all the time steps, we are actually prescribing a function to this, okay? So that's why we are rewriting this part, okay? So u0 t equals to big U because we are taking the wheel part. Cosine omega t. Okay, so we are assigning the things in here. Okay. So this can be affected into the domain, the white region. Given C is larger than 0 in this case. Okay, why do we want to do that? We want to put U back to the advection equation. Okay. Iota omega t plus c partial x u x, and then e minus iota omega t equals to 0. Okay, this is the analytical form, and then we do the differentiation, and then this is what we get. It still depends on x, but I'm not writing that here. Okay, partial u partial x. We cross out the e to the power of minus iota omega t. Okay, and then we do the integration. Okay, and then we know that u depends on x, right? U naught, it's a constant, and then e iota omega over c x, which equals to e iota kx, because we know that omega over c equals to k. This is the dispersion relation for the analytical solution. Okay, and at the left boundary or inflow boundary, u 0 equals to u naught e to the power of 0, which equals to u naught. Okay, now we have the value of u naught, or u depends u when x equals to 0. Okay, hence x equals to u 0 e to the power of iota kx. Okay, now we have an expression for the x dependent part. This is x, right? Okay, so the full analytical or continuous solution is u xt equals to u naught, or u 0, and then the real part of e iota kx minus omega t, where omega equals to kc. Okay, so now we have the expression for u for this one. Okay, so this is how we arrive at this. So it's some function representing the change in space in here, because they will determine the values in this white region. Okay, and then we've written this equation in terms of the u naught, which is the value in here. Okay, and then the wave function, or the wave solution. It will determine all the values in this region. Okay, it's called inflow boundaries, and here we consider the finite difference version of advection equation, we are just writing the advection equation in the discrete version. So this is not the discrete version, this is the continuous or analytical, the original advection equation, discrete form. And then we assume the discrete form in space, only in space. Okay, t is still here. Okay, we change this analytical solution in terms of in the discrete solution, in the discrete version. Okay, and then this is for comparison, the analytical solution. If you compare, this one is what we got from the last slide. And then we put this into the discrete version, and then we can put this into the original advection equation to find the dispersion for the analytical form, which is the true dispersion. And then we want to find the dispersion for this kind of discrete version of advection equation. Okay, so how do we do that? If you can do it on your own, you don't need to see my calculations here. Finite difference. Okay, this is the discrete version, only discrete in space. Because if we put the discrete in time, then we will not find the dispersion relation. Iota omega t over 2 delta x. Okay, and then we do differentiation here. Iota kx plus c iota k I plus 1. Remember that we are substituting the discrete solution for this discrete advection equation. Delta x equals to 0. Okay, and then we cross out something. Plus c, then e iota k delta x minus c minus iota k delta x equals to 0. And then I'm writing everything here. Assume that you already know this, okay? Sine theta plus iota sine theta, and okay, so now what do we have? That x omega iota plus 2z sine k delta x, because we have used the equation here. Kx iota 0, and then we cross out the iota, we get the dispersion relation for the discrete version, for the discrete solution. Okay, and then if we do something on this side, we will have the omega in terms of k in this way. So this is what we have in the slide here, this one. And then this is the true dispersion. This is what we want to achieve. And then we change the expression in terms of omega delta x over c so that we can compare the values for these two methods. This is what we want to achieve. This is what we get from the finite differencing. So usually when we are talking about dispersion, this is the relationship. So the frequency is expressed in terms of a function of k. But now we are changing this, including delta x and c on the left side. So it's just we have just done some small mathematical maneuvering here. Okay, this is still a dispersion relation. So this is the result. So this is the true dispersion, what we want to achieve, and this is what the finite differencing is giving you. And we can see that for a value of k, for a value of omega, okay, if we pick a value here, for example 0.5 in here, we will have two k's. One is hitting here, and then the other one is hitting here. So what we want to say is that we want to stay in this region between 0 and pi over 2, because you can see that the group velocity is still positive comparing to the true dispersion relation. We want to stay in this zone. This zone is called the physical mode because they make sense. They're in the same direction as the true dispersion. And on this side, the group velocity is going backward comparing to the phase velocity. So we have already explained this in the last few lectures. So if you forgot the idea, please refer to, I think, lecture 6. Okay. And this is, for this region, we will call it computational mode because it doesn't make sense. Anything doesn't make sense. It's coming from the method. It's coming from the finite differencing method. So this is the computational mode K2, and K1 we'll call it physical mode. Delta K1 is the physical mode, I delta x minus omega t, and then the computational mode ui iota K2 I delta x minus omega t. And then we know that K2 delta x equals to pi minus K1 delta x. Okay, so we can rewrite, so this one U naught, we rewrite the computational mode in terms of K1, iota pi I minus K1 I delta x minus omega t, okay, equals to U naught minus 1 to the power of I RE minus K, K1 okay. So I still want to write something down here. This is due to the fact that e to the power of iota I pi equals to minus 1 to the power of I. Okay, so now what do we have here? What we have here is that we know that this term will give you a very weird signal because it depends on I, right? And then it flips the sign, which means that if this is I, then your signal will be like this. Okay, so if your signal, okay, I better write it better. If your signal originally is like this, it will not look like this because of this term. It will look like this. Okay, it will look like this. Okay, which means that it doesn't make sense, which means that this is the computational mode. It's not physical. It's coming from the method that we use. The method that we use is giving us this shape in the dispersion relation. And that's why we will have a signal looking like this. So the signal will be looking like this. Okay, this is what I meant. When the signal should be looking like a wave function. Okay, and it should not happen in the nature, right? So it's totally fake or totally wrong, the wrong solution. It's not the solution that we want. Okay, so I think I've just explained this. So if you have some signal originating from I equals to 0, sorry, this is I equals to 0. This is a typo here. The source of influence is coming from I equals to 0, and then on the right side you have the physical mode traveling because C is positive, okay, and its wave number is K1. And then on the other side you have an opposite, like a mirror image of this, except that you have the sign oscillating, same the term here. So your signal should have been a mirror image of this, but because of this term, you have an oscillating sign here. And then it's traveling in a different direction comparing to this one. It's positive, so it's traveling over the left side, okay, which is something we don't want. So one thing we want to remember is that if we want to make the discrete dispersion relation look like the true dispersion relation, we can make delta x very small, so that because we know that if delta x is very small, if this term is very small, then sine k delta x equals to k delta x. It's also coming from Taylor series expansion. Okay, so next we talk about the outflow boundaries. What are the outflow boundaries in here? Okay, the goal in here that we want to achieve is that we have no computational or reflected signal or weird signals due to the finite differencing. Why do we want to say that? So we are inputting values in here. We have some values in here at the beginning, and then when the values hit this wall, this is a wall, right? It's the outflow boundary. When your signal is hitting this wall, we don't want any reflection or weird signals coming from this wall, okay? So how do we make use of the finite difference form of the advection equation? So if what we have here is the leapfrog scheme, which is the center in time and then center in space for the advection equation, and if the domain has nx plus 1 points, we will have the boundary at I equals to 0, and then I equals to nx, and then we have the time step here, n equals to a, and then the next time step, and then the next time step. Okay, so in here, I equals to 0, which is the inflow boundary. It's given as a function of time, so we have already covered this. And then for I equals to 1, and then so on, it will be determined by the values at I equals to 0, right? And then the values next to it. Okay, and then at the second last column here, the values at the outflow boundary will determine the second last column in here. So, which means that in order to predict the values in here, we need to know the values in here before we do any kind of calculation. So it's called the computational boundary condition, and xt depending on t. So it's just similar to what we have just done for this column. We need to decide the value here. It's a matter of choice. Okay, so there are different options. There are many, many more options comparing to these 5 methods. I have just introduced a few methods to you so that if you want to read further, you will be able to. Okay, so there are different options, different methods to consider in here. So the first method, we're determining the value at I equals to nx in here. So method 1 is that unx equals to constant in time. You can't just say that it's 0 all the times. Okay, and then method 2 is that we can decide that the values of these two are the same. So when you do the last step in here, you will only have one unknown, right? If they are the same, then if you do center differencing, then you will only have one unknown. It will be easy. It will be easier, okay? And then the third method is that we assume that the change at this location would be the same as the change at this location. So the change in time, okay? So it's just depend on your choice. So we know that when we do finite differencing, we will have the computational mode and then the physical mode. So we assume that the final solution will be the combination of a linear combination of the physical mode and then the computational mode. Modes. Okay, and then u. So this is the solution for the discrete version equals to u naught iota k I delta x minus omega t plus r minus 1 to the power of I, and then e minus iota k. We have done this expression in the last slide. Okay, so we know that this is the physical mode, and this is the computational mode. And R is a constant determining the true the virtual reflection rate at the boundary for the computational mode. Okay, so the hope is that we can keep this value as small as possible. The hope is to have R equals to 0. Of course, we don't want any computational, it's fake, it's not physical. So the first method in the slide, method 1, for the convenient reason, we assume that nx is an even number, and u and x equals to 0, because for the first method, it's constant, right? We are setting a boundary as constant. So u and x equals to u naught e iota k and x delta x minus omega t plus r minus 1 and x e minus iota k and x delta x, okay, plus omega t equals to 0. Okay, and then we can do something here. So it's constant equals 0. So we can do something here. E iota k and x delta x plus r e minus, because we know that nx is an even number, so this term will be minus 1. This term will be 1. Okay, e minus iota k and x k and x delta x e minus iota t equals to 0. So we have taken out the time, the term here. Okay, and then we know that this term is not equal to 0, which means that this term should be equal to 0. Okay, and then r equals to minus e iota k and x delta x over e minus iota k and x delta x equals to minus e iota 2 k and x delta x. So what we know here is that this one equals to minus cosine 2k and x delta x minus iota sine 2k and x delta x. Okay, it's a complex number, but we know the magnitude of this. So if you don't know how to find the magnitude of a complex number, please Google that. Okay, I'm not going to explain that again. Okay, so which means that the incident wave is totally reflected, and the computational modes amplitude equals to physical modes. Okay, this is something we don't want. We want to eliminate this term. But now it's as large as the physical mole in here. Okay, it's something we don't want. Okay, so the next method is method 2. I'm not going to explain all the methods in here, just these 2 methods, I think. Okay, assume, again, for the convenient reason, we assume that nx is an even number, and unx equals to unx minus 1, which is method 2. Okay, and then we can do the calculation nx minus 1 delta x minus omega t plus r minus 1 nx minus 1 e to the power of minus iota k nx minus 1 delta x plus omega t. Okay, so this is u and x. This is u and x minus 1, and then it equals to e iota k and x delta x minus omega t plus r and x e. So this is u and x, and they are equal. Okay, now we can do we can cross out something in here, e to the power of I k n x delta x e minus iota k delta x x delta x iota k delta x e minus iota omega t equals to e iota k n x delta x plus r and then we can cross something out in here. Divided, okay, we cross this. And then I think we can cross something else. E to the power, okay, we can cross this. And then we divide the whole equation. Divide the whole equation by e to the power of minus iota k n x delta x. Okay, and then what we can get is iota 2 k n x delta x, and then e iota k delta x minus r e iota k delta x equals to e iota 2k n x delta x plus r. Okay, and then we can take out the r, the value of r, e to the power of iota 2k n x delta x, and then e minus iota k delta x plus minus 1. 1 plus e to the power of iota k delta x. Okay, so how do we explain this expression of R? We can do some mathematical maneuvering, but this part is optional. Okay. The gray text is optional in here. With the identities. Z1, Z2 equals to the magnitude of Z1 and Z2. And tangent theta 2, theta over 2 equals to, I think you should have learned this in your math course. And then C1 and C2 and Z2 are complex numbers. Okay, we can rewrite this term e to the power of iota 2 k n x delta x. Oh, we know that the magnitude of this is 1, and then 2 is that k delta x minus 1 e iota k delta x plus 1. We know that this equals to and provided that this theta equals to k delta x over cosine square theta plus 2 cosine theta plus 1 plus sine square theta. Okay, and then cosine theta 2 plus 2 cosine theta tangent theta over 2 which equals to tangent k delta x over 2. Okay, we can make use of these two expressions to rewrite the value of R in here. Okay, the magnitude of R actually is what we want to look at. Okay, so if we want to look at the magnitude of R, we are actually looking for the magnitude of this one and also this one, right? So for the first expression, we can use this to find the magnitude of this one, and then for this is for the second one. Okay, so now we can know the magnitude. So the optional part is this region. Now let's go back to the non-optional part. Okay, so R, the value of the magnitude of R equals to tangent k delta x over 2. Okay, and why do we want to express the magnitude of R in terms of delta x and k? It means that the magnitude of reflection will be depending on the size of your waves and on the choice of delta x that you choose. Okay, and for lambda equals to 4 delta x, the magnitude of the reflection is 1, which is something we don't want. Okay, we want to make this as small as possible. Okay. And the physical mole exists when your wave number is larger than 4 delta x. For large wave number, the reflection will be close to 0. Okay, which means that this kind of boundary condition is favorable for long waves. Long waves are not falsely reflected with this boundary condition. With this. So it can be used as open boundary. What does it mean by open boundary? It means that the waves can travel through this boundary freely. Okay. And for method 3, you can do the similar calculation with method 1, and we will find that the reflection equals to 1, which is also something we don't want. Okay, this is as large as the physical mole. And then method 4 also, oh sorry, this is 4. For method 3, sorry about this. For method 3, it's similar to method 2. Considering a discrete finite difference here in space first. And then it will also be equal to k delta x tangent k delta x over 2. If you look at the paper, you will find that there are more than 5 methods in choosing the boundary condition. If you're interested, you can look at the paper, the journal paper. I put the link in the slide. So for method 5, it's equivalent to setting the second derivative to 0 at the wall. And then the magnitude of the reflection is k delta tangent square k delta x over 2. Okay. So this is starting with the simulation with the box signal in the middle, and then you're familiar with this exercise. It's in the lecture 5, exercise 3, leapfrog boundary condition. And then if we are setting the value in here with a constant 0, then your box signal will travel to the wall and then coming back in the computational form. You can see that. Okay, I have the simulation for this. So you can see that with the advection equation is travel to the right, and then you see some very small computational mole here, but when it hits the wall, it becomes the computational mole oscillating in with I. Okay, the magnitude of that is decreasing, but it's all wrong. It's not something we want. Okay, so you can see the wrong decision you make in making the boundary condition, and then there is something we don't anticipate in the result. So this signal originally should travel through this wall and then never coming back. Okay, so I have taken the graph from the papers in here, and I think they have listed 8 different methods. I have just shown you the first 5 methods so you can see the result. This is the after the reflection. This is the original signal, what it should have been look like, and then the dashed line is the computational mode. Okay, if you do the calculation after 100 iterations, 100 n, n equals to 100, and then you can see that the noise is reflected from the outflow boundary. And for the second one, it's better. And then for the third and the fourth one, you can still see some computational modes that we don't want. And there are many more methods. You can look at the papers in here. Okay, so next we talk about the advection on nested grids. What does it mean by nested grids? I think I've explained this in the last portion of this lecture. So if you have a nested grid inside the lower resolution model, you have a higher resolution model in here. By higher resolution, we mean smaller grid size because we have more representation in here. It's with a higher resolution. So in here, I want to study if we have some signal oscillating in the higher resolution in the nested grid, and then it's attempting to going through the wall and then going to the lower resolution model. So our model, our signal incident wave is originally having the wave number k0, and then when it travels through the wall, the wave number changes to k, is the transmitted wave, this part. And then we also have the reflected wave. So and then we set the index I equals to 0 at the wall, and then the index with the minus numbers is with the higher resolution, and then the index with the positive number is representing the index in the lower resolution outside. Okay, so if we are having the signal, what change will we have? It's influenced by the change of this resolution. Okay, it's totally due to the method. It's not because of the physics. Okay, so for I less than 0, which means that if we are at the high resolution side, this is the signal. We have the physical mode in terms of k0, and then we also have the computational mode. We have the computational, the term for the spatial oscillating term, and then the magnitude of this reflection. This is the term that we don't want. Okay, and then we also have the dispersion relation on this side, on the green side. And then for the I positive side, we can express the whole equation with this wave solution with the space d2, which is the delta x in this model, and then with the wave number k. And because the signals is traveling through this wall to the right side, we assume that there's no reflection happening here, because reflection means that it's reflected back. So we only have the reflection in here. And then we have the expression for this is dispersion relation on the right hand side. Okay. So this part is optional. The slide in here is not optional, but calculation for this line is optional. Okay. Advection on nested grid. And we consider C larger than 0. Okay, one thing, it should be the same on both sides. Frequency must be the same. In both parts. Okay, and then we can rewrite the whole equation equals to, and we write the sine k d2 d1 because this determines the dispersion relation, so we rewrite this. Iota sine k d2. And then we rewrite this in terms of A plus iota A. Okay, so I will explain two cases in here. Because we only have D2 larger than D1. So this is case 1, and then we'll separate case 1 into two cases in this lecture. Waves traveling from finer grids, higher resolution, to coarser grids. Okay, and then case 1a is that we have the value of A larger than 1. And then KD2 is a complex number. Okay, because if you look at this one, if A is larger than 1, then normally we should not have any values for KD2 because it's not permitted. But we can make KD2 a complex number to fulfill this. Okay. I don't know if you have learned this in the math course, so that's why this is optional. E to the power of iota k d2 a. We have taken out the iota in both terms, and then E iota pi over 2 . Okay, and then for I larger than 0, larger than or equal to 0, which is on the right hand side, U I equals to R A plus or minus C squared minus 1 to the power of I, and then E iota pi over 2 minus omega t. Okay, we have taken something out from the x depending term, and then there are two solutions here. A plus A squared minus 1 is larger than 1, and then A minus A squared, because A is larger than 1, so we know that this one is less than 1, and then this one is larger than 1, and then this one is less than 1, sorry. Okay, so we choose this one because it's stable. Because this term is controlling the this term is controlling the growth and decay of the solution, or controlling the stability of the solution. Okay, and then only a minus a squared plus 1 root is accepted, since a is larger than 1. And then we know that the amplitude, if this is I, and we know that the amplitude of this, okay, the amplitude decays as I increases. Okay, and then for case 1b, a is less than 1 and k d2 is real, and we know that k d2 is less than pi over 2 because sine k d2 is less than 1, right? It's the physical mole. We want to make it the physical mole. Okay, so it's less than pi over 2. And then we know that lambda should be equal to 2 pi over k, which is larger than 4 d2. To stay in the physical zone. Okay, so for I larger than 0, ui equals to r e iota I sine minus 1a minus omega t. Okay, since omega 1 equals to omega 2 and d2 larger than d1, and then we have the discrete dispersion relation over d1 over sine k d2 over d2 equals to 1. This is coming from the dispersion relation. Okay, and then we multiply the whole equation by k over k naught on both sides, and then we can have k equals to k naught equals to so this is the dispersion relation that we have. It's larger than 1 because we know that d2 is larger than d1. Okay, so to draw a schematic diagram for this, sorry about my drawing. Okay, and then this is pi over 2. So we want to stay in this region because it's the physical mole region, and then we have the 2 kd. This is omega delta x over c. The first one is omega d2 over c, and then omega d1 over c. And then this one is representing the wave with k d2 and then k naught d1. And this value is sine k naught d1. It's hard to explain this relation, so that's why I'm drawing you this graph. So that you know why this expression is larger than 1. And this is k delta x. Okay, so that's why we have arrived at this, which means that if we want to keep the frequency the same for this wave, k will increase. Okay, originally we have the wave number k naught here, and then the k, when your waves is traveling through this wall, the k is becoming larger comparing to the original k naught. It's larger than 1, right? Which means that your waves, your transmitted waves have higher wave numbers or smaller delta. It's something that we don't want because it's not physical. It's due to the boundary in here. Okay. And the reverse situation where we are having the wave traveling from the lower resolution into the nested domain is not studied here because it's with a lot of difficult math, so I'm not going to include that in this course. And the analysis with the reflection is also not done in here. If you're interested, please talk to me. Okay,